Corrosion under insulation, or CUI, damage mechanisms as a part of uniform or localized loss of thickness. Description of corrosion under insulation based on API 571, corrosion of piping, pressure vessels and structural components resulting from water trapped under insulation or fireproofing. Corrosion under insulation, or CUI, is a severe form of corrosion that affects metallic equipment such as piping systems, pressure vessels, and tanks, which are encapsulated with thermal insulation. This type of corrosion occurs when water or moisture infiltrates the insulation and makes contact with the underlying metal surface, leading to external corrosion beneath the insulation. Key points about corrosion under insulation damage. Number 1 is what causes. CUI is primarily caused by moisture intrusion, which can come from environmental sources like rain, condensation, or process leaks. The presence of oxygen and dissolved species within the insulation also contributes to the corrosion process. Number 2 is affected materials. Common materials affected by CUI include carbon steel, stainless steel, and alloy steel. Number 3 is, what is the impact of corrosion under insulation, or CUI? CUI can lead to significant structural integrity loss, increased maintenance costs, safety hazards, production downtime, and environmental risks. Number 4 is, what is the detection and mitigation method to be used? Detecting CUI can be challenging due to its hidden nature. Advanced technologies, such as robotics and specialized inspection methods, are increasingly used to identify and mitigate CUI effectively. Corrosion under insulation, or CUI, is a specific type of corrosion that occurs on the surface of equipment and piping that is insulated. It is particularly problematic in industrial environments where insulation is used to maintain temperature, protect against heat loss, or reduce condensation. CUI is often difficult to detect because it occurs beneath the insulation, making early identification and assessment challenging. Characteristics of corrosion under insulation damage includes. Number 1 is localized corrosion. CUI typically leads to localized pitting or general corrosion beneath the insulation, which can significantly compromise the structural integrity of the metal components. Number 2 is moisture accumulation. CUI is primarily driven by the presence of moisture trapped between the insulation and the substrate. This moisture can arise from several sources, including condensation, leakage, or inadequate insulation installation. Number 3 is temperature variability. Insulation is often applied to systems operating at varying temperatures, and temperature fluctuations can exacerbate corrosion. As temperatures rise and fall, condensation may form on cooler surfaces, providing an ideal environment for corrosion. Number 4 is material dependence. The susceptibility to CUI varies based on the type of material involved. Carbon steel, for example, is particularly vulnerable, whereas stainless steels and other alloys may have different thresholds of resistance depending on their grades. Number 5 is degradation of insulation. Over time, insulation materials themselves can degrade or become damaged, allowing more moisture to penetrate and facilitating CUI. Additionally, insulation that retains water becomes a breeding ground for microbial activity, which can contribute to corrosion. Number 6 is difficult inspection. Inspecting for CUI requires specialized techniques such as ultrasonic testing, radiography, or advanced non-destructive testing methods. Traditional visual inspections are often insufficient, as the corrosion occurs hidden from view. Number 7 is cost implications. Failure to address CUI can lead to significant maintenance costs, premature equipment failure, and production downtime. This can impact safety, environmental compliance, and overall operational efficiency. Corrosion under insulation, or CUI, can occur over a range of temperatures, but it is particularly prevalent within specific temperature ranges. The susceptibility to CUI is generally recognized between 32 degrees Fahrenheit, or 0 degrees Celsius, and 250 degrees Fahrenheit, or 121 degrees Celsius. Here's a breakdown of how temperature affects CUI and its likelihood. Number 1 is key temperature ranges for CUI. Number A of the key temperature ranges for CUI is low temperature, 32 degrees Fahrenheit to 140 degrees Fahrenheit or 0 degrees Celsius to 60 degrees Celsius. This low temperature range is critical as cold surfaces can attract moisture through condensation, especially in humid environments. Insulation systems may not be designed to prevent moisture ingress at these temperatures. Number B of the key temperature ranges for CUI is moderate temperature, 140 degrees Fahrenheit to 200 degrees Fahrenheit or 60 degrees Celsius to 93 degrees Celsius. The risk of CUI is heightened within this range due to the ideal conditions for condensate formation. Temperatures approaching the boiling point of water can lead to frequent condensation events, promoting corrosion. Number C of the key temperature ranges for CUI is high temperature, 200 degrees Fahrenheit to 250 degrees Fahrenheit or 93 degrees Celsius to 121 degrees Celsius. CUI risk remains significant as moisture can still condense and be retained under insulation. While temperatures in this range can hinder the presence of some types of liquid water, the potential for vapor condensation exists. Number D of the key temperature ranges for CUI is above 250 degrees Fahrenheit or 121 degrees Celsius. At temperatures above this threshold, the risk of direct moisture accumulation diminishes due to evaporation, but corrosion can still occur through other mechanisms, such as exposure to aggressive environments or insulation degradation. Number 2 is additional considerations of how temperature affects CUI and its likelihood, includes. Number A of additional considerations is material type. Different materials react differently to temperature changes, and certain alloys may be more resistant to CUI in high-temperature scenarios, whereas others may be more prone to degradation. Number B of additional considerations is environmental conditions. High humidity, exposure to salts or other corrosive agents, and frequent temperature cycling further influence CUI risk, regardless of the specific temperature range. In conclusion, while CUI can fall within a broad temperature range primarily between 32 degrees Fahrenheit, or 0 degrees Celsius, and 250 degrees Fahrenheit, or 121 degrees Celsius, the most significant risk typically occurs between 140 degrees Fahrenheit, or 60 degrees Celsius, and 200 degrees Fahrenheit, or 93 degrees Celsius, where moisture retention under insulation is most conducive to corrosion processes. Proper design, maintenance, and inspection strategies are essential to manage and mitigate this risk effectively. Corrosion under insulation affected materials based on API 571, carbon steel, low alloy steels, 300 series SS, and duplex stainless steels. Corrosion under insulation primarily affects the following materials. Number 1 is carbon steel. Widely used in industrial applications, carbon steel is highly susceptible to CUI, especially in the temperature range of -4 degrees Celsius to 175 degrees Celsius. Number 2 is stainless steel. Although more resistant to corrosion than carbon steel, stainless steel can still suffer from CUI, particularly in the temperature range of 50 degrees Celsius to 175 degrees Celsius. Number 3 is alloy steel. Various alloy steels, which are used for their enhanced mechanical properties, can also be affected by CUI. These materials are commonly found in piping systems, pressure vessels, tanks, and other insulated equipment in industrial settings. Proper maintenance and inspection are crucial to prevent and mitigate CUI damage. Corrosion under insulation, CUI, can affect a variety of materials used in industrial applications, with the most affected typically being metals. Here's a breakdown of the materials commonly impacted by CUI. Number 1 is carbon steel. Carbon steel description: the most commonly affected material due to its prevalence in piping and structural components. Carbon steel vulnerability: carbon steel is highly susceptible to both localized corrosion, such as pitting, and general corrosion when moisture is trapped under insulation. Number 2 is low alloy steel. Low alloy steel description: used in higher strength applications or where resistance to certain environmental factors is required. Low alloy steel vulnerability: similar to carbon steel, low alloy steels can develop CUI, particularly in poorly maintained conditions. Number 3 is stainless steel. Stainless steel description, used for its corrosion-resistant properties, particularly in food, chemical processing, and marine environments. Stainless steel vulnerability, while generally more resistant to corrosion, certain grades, especially those with lower nickel content, such as 304, can experience CUI if chlorides are present or if they are improperly passivated. Number 4 is copper and copper alloys. Copper and copper alloys description, commonly used in plumbing and heat exchange applications. Copper and copper alloys vulnerability, while copper itself tends to resist corrosion, CUI can still occur with the presence of moisture and aggressive contaminants. Number 5 is aluminum. Aluminum description, lightweight and corrosion-resistant material often used in construction and chemical processing. Aluminum vulnerability, aluminum can corrode under insulation in specific environments, particularly when chlorides or other corrosive agents are present. Number 6 is nickel alloys. Nickel alloys description, alloys with nickel, like Inconel or Monel, are used in demanding applications due to their high strength and corrosion resistance. Nickel alloys vulnerability, although they are resistant to many forms of corrosion, these materials can still be susceptible to CUI in extreme environments with aggressive agents. Number 7 is cast iron. Cast iron description, often used in pipes and structural elements. Cast iron vulnerability, cast iron can be affected by CUI, especially in flanged joints and areas where moisture can accumulate. Factors influencing susceptibility of corrosion under insulation includes. Number 1 is type of insulation. Different insulation materials can absorb moisture differently, impacting the likelihood of CUI. Number 2 is environmental conditions. Humidity, temperature fluctuations, and the presence of contaminants, like chlorides, can significantly increase susceptibility. Number 3 is physical condition. Damaged or improperly installed insulation can allow moisture infiltration, promoting CUI. In conclusion, while a range of materials can experience CUI, carbon steel stands out as the most vulnerable. Protective measures, including suitable insulation designs, proper maintenance, and the use of corrosion-resistant alloys, are vital in mitigating the risks associated with CUI across various materials. Regular inspections and monitoring are also essential in identifying potential CUI issues before they lead to significant damage. Corrosion under insulation critical factors based on API 571. Number A, it affects externally insulated piping and equipment and those that are in intermittent service or operate between 10 degrees Fahrenheit, or -12 degrees Celsius, and 350 degrees Fahrenheit, or 175 degrees Celsius, for carbon and low alloy steels. 140 degrees F, or 60 degrees Celsius, and 400 degrees F, or 205 degrees Celsius, for austenitic stainless steels and duplex stainless steels. Corrosion rates increase with increasing metal temperature up to the point where the water evaporates quickly. For insulated components, corrosion becomes more severe at metal temperatures between the boiling point 212 degrees Fahrenheit, or 100 degrees Celsius, and 350 degrees Fahrenheit, or 121 degrees Celsius, where water is less likely to vaporize and insulation stays wet longer. Number C, design of insulation system, insulation type, temperature and environment are critical factors. Number D, poor design and/or installations that allow water to become trapped will increase CUI. Number E, insulating materials that hold moisture, wick, can be more of a problem. Number F, cyclic thermal operation or intermittent service can increase corrosion. Number G, equipment that operates below the water dew point tends to condense water on the metal surface, thus providing a wet environment and increasing the risk of corrosion. Number H, damage is aggravated by contaminants that may be leached out of the insulation, such as chlorides. Number I, plants located in areas with high annual rainfall or warmer, marine locations are more prone to CUI than plants located in cooler, drier, mid-continent locations. Number J, environments that provide airborne contaminants such as chlorides, marine environments, cooling tower drift, or SO2, stack emissions, can accelerate corrosion. Corrosion under insulation is a complex form of corrosion influenced by several critical factors. Understanding these factors is essential for effective prevention, monitoring, and mitigation strategies. Here are the main critical factors that contribute to CUI, includes. Number 1 is temperature. CUI temperature influence. The temperature of the substrate significantly affects CUI. CUI is most likely to occur in the range of 32 degrees Fahrenheit, or 0 degrees Celsius, to 250 degrees Fahrenheit, or 121 degrees Celsius, with a higher incidence noted between 140 degrees Fahrenheit, or 60 degrees Celsius, and 200 degrees Fahrenheit, or 93 degrees Celsius. CUI temperature consequences. Elevated temperatures can increase moisture retention and accelerate corrosion rates. The number 2 of the main critical factors that contribute to CUI is moisture. CUI moisture source. Moisture can originate from condensation, leaks, rain, or environmental humidity. CUI moisture impact. The presence of moisture under insulation is a primary catalyst for CUI. Trapped moisture creates an environment conducive to corrosion. Number 3 of the main critical factors that contribute to CUI is insulation material. CUI insulation material type. Different insulation materials have varying capacities for moisture retention. CUI insulation material effects. Fiberglass or mineral wool may absorb moisture, while closed-cell insulation may resist it. The choice of insulation can significantly impact the likelihood of CUI. Number 4 of the main critical factors that contribute to CUI is environmental conditions. CUI environmental conditions factors, humidity levels, temperature fluctuations, and atmospheric conditions, such as coastal environments, industrial emissions, can all contribute to CUI. CUI environmental conditions corrosive agents, presence of contaminants, such as chlorides from coastal air or industrial pollutants, can exacerbate corrosion effects. Number 5 of the main critical factors that contribute to CUI is surface condition. CUI surface condition preparation. The condition of the metal surface prior to insulation application matters. Rough, unclean, or oxidized surfaces are more prone to corrosion. CUI surface condition coatings. Inadequate or damaged protective coatings can allow moisture to contact the metal surface. Number 6 of the main critical factors that contribute to CUI is mechanical damage. CUI mechanical damage sources. Impact from vibrations, physical damage during maintenance, or improper insulation installation can compromise insulation integrity. CUI mechanical damage effects. Damaged insulation can permit moisture ingress, increasing the risk of CUI. Number 7 of the main critical factors that contribute to CUI is operation cycles. Number 7 of the main critical factors that contribute to CUI is operation cycles. CUI operation cycles. Continuous operation. Continuous operation at elevated temperatures might reduce water accumulation but does not eliminate the risk. Number 8 of the main critical factors that contribute to CUI is corrosion rate of material. CUI material selection. The inherent corrosion resistance of the selected materials plays a crucial role. For example, carbon steel is more susceptible to CUI compared to stainless steel or nickel alloys. CUI corrosion rate of material. Alloy composition. The composition and structure of the alloy can influence resistance to CUI. Number 9 the main critical factors that contribute to CUI is inspection and maintenance practices. CUI inspection and maintenance practices. Regular monitoring. Lack of frequent inspections can allow CUI to progress unnoticed, increasing the likelihood of failure. CUI inspection and maintenance practices. Maintenance. Proactive maintenance, including inspecting insulation, fixing leaks, and replacing damaged sections, is vital for CUI management. Number 10 of the main critical factors that contribute to CUI is preventive measures. CUI preventive measures. Design choices. Designing systems that minimize moisture retention, such as using vapor barriers and drainage features, can help mitigate CUI. CUI preventive measures cathodic protection. In some applications, cathodic protection systems can be employed to reduce corrosion rates. In conclusion, CUI is a multifaceted issue influenced by numerous interrelated factors. Effective management requires a comprehensive understanding of these factors to implement appropriate design, maintenance, and monitoring strategies. Regular inspection and proactive measures are key to minimizing the risk and impact of CUI in industrial settings. Corrosion under insulation affected units or equipment based on API 571, Number A. All insulated piping and equipment are susceptible to CUI under conditions noted above, even on piping and equipment where the insulation system appears to be in good condition and no visual signs of corrosion are present. Number B. Examples of locations where CUI can occur are listed below. Number 1 is CUI can be found on equipment with damaged insulation, vapor barriers, weatherproofing or mastic, or protrusions through the insulation or at insulation termination points such as flanges. Number 2 is equipment designed with insulation support rings welded directly to the vessel wall, no standoff, particularly around ladder and platform clips, and lifting lugs, nozzles and stiffener rings. Number 3 is piping or equipment with damaged/leaking steam tracing. Number 4 is localized damage at paint and/or coating systems. Number 5 is locations where moisture/water will naturally collect, gravity drainage, before evaporating, insulation support rings on vertical equipment, and improperly terminated fireproofing. Number 6 is vibrating piping systems that have a tendency to inflict damage to insulation jacketing, providing a path for water ingress. Number 7 is dead legs, vents, drains, and other similar items. Number 8 is pipe hangers and other supports. Number 9 is valves and fittings, irregular insulation surfaces. Number 10 is bolted-on pipe shoes. Number 11 is steam tracer tubing penetrations. Number 12 is termination of insulation at flanges and other piping components. Number 13 is insulation jacketing seams located on the top of horizontal piping or improperly lapped or sealed insulation jacketing. Number 14 is termination of insulation in a vertical pipe. Number 15 is caulking that has hardened, has separated, or is missing. Number 16 is bulges or staining of the insulation or jacketing system or missing bands. Bulges may indicate corrosion product buildup. Number 17 is low points in piping systems that have a known breach in the insulation system, including low points in long unsupported piping runs. Number 18 is carbon or low-alloy steel flanges, bolting, and other components under insulation in high-alloy piping systems. Number 19, locations where insulation plugs have been removed to permit piping thickness measurements on insulated piping and equipment should receive particular attention. These plugs should be promptly replaced and sealed. Several types of removable plugs are commercially available that permit inspection and identification of inspection points for future reference. Number 20 is the first few feet of a horizontal pipe run adjacent to the bottom of a vertical run. Corrosion under insulation, or CUI, can affect a wide range of units and equipment commonly found in industrial settings. Here's a breakdown of the types of equipment that are typically prone to CUI damage. Number 1 is piping systems. Piping systems description: pipelines transporting liquids, gases, and steam. Piping systems impact: CUI can lead to significant structural integrity issues, leaks, and failures, particularly in carbon steel, low-alloy steel, and certain stainless steels. Number 2 is tanks and vessels. Tanks and vessels description: storage tanks and pressure vessels used in chemical processing, oil and gas, and water treatment. Tanks and vessels impact: insulated tanks can suffer CUI, leading to corrosion at the base and around fittings or nozzles. Number 3 is heat exchangers. Heat exchangers description: equipment that transfers heat between two or more fluids. Heat exchangers impact: the insulation can trap moisture, leading to corrosion on the shell, pipes, and other components, affecting efficiency and safety. Number 4 is valves. Valves description: devices that regulate the flow of fluids, usually a part of piping systems. Valves impact. Valve bodies and internals can corrode under insulation, leading to leaks and operational failure. Number 5 is flanges and fittings. Flanges and fittings description: connection points for pipes, usually made from carbon steel or stainless steel. Flanges and fittings impact. These components can be vulnerable to CUI, particularly at joints where moisture can accumulate. Number 6 is supporting structures. Supporting structures description: structural supports such as brackets, hangers, and supports for piping or equipment. Supporting structures impact. These components, often made from carbon steel, can corrode when insulated, especially if moisture is trapped. Number 7 is boilers. Boilers description: equipment used to generate steam or heat water. Boilers impact. Insulated boilers can also experience CUI, particularly in areas where vapor collection occurs. Number 8 is chillers and cooling towers. Chillers and cooling towers description: heat exchange equipment used in HVAC systems. Chillers and cooling towers impact. CUI can occur on piping and structural elements associated with these systems, particularly when moisture is present. Number 9 is compressor and pump casings. Compressor and pump casings description: enclosures for compressors and pumps that move fluids in various processes. Compressor and pump casings impact. CUI can lead to failures, impacting operational safety and performance. Number 10 is electrical equipment enclosures. Electrical equipment enclosures description: housings for electrical equipment, including junction boxes and control panels. Electrical equipment enclosures impact. Poor insulation design that traps moisture can lead to corrosion of electrical enclosures, impacting reliability and safety. Number 11 is steam and condensate lines. Steam and condensate lines description: lines that transport steam and condensed water in processes such as heating. Steam and condensate lines impact. These lines can suffer from CUI, especially when insulating materials are not correctly installed or maintained. Number 12 is refrigeration units. Refrigeration units description: equipment that removes heat from a designated area, often using cooling coils. Refrigeration units impact. Insulated cooling coils can experience CUI, leading to decreased efficiency and failure. In conclusion, CUI poses significant risks to various types of industrial equipment. Regular inspections, effective insulation design, moisture management, and proper maintenance practices are crucial to minimizing the risk of CUI in these units. Understanding which equipment is vulnerable helps in developing targeted preventive measures to enhance the longevity and reliability of industrial systems. Corrosion under insulation: appearance or morphology of damage based on API 571. Number A. Carbon and low alloy steels are subject to localized pitting corrosion and/or localized loss in thickness. Number B. 300 series SS are also subject to stress corrosion cracking, SCC, if chlorides are present, while the duplex SS are less susceptible. Number C. 300 series SS and duplex SS are subject to pitting and localized corrosion. For 300 series SS, specifically in older calcium silicate insulation, known to contain chlorides, localized pitting and chloride stress corrosion cracking can occur. Number D. After insulation is removed from carbon and low alloy steels, CUI damage often appears as loose, flaky scale covering the corroded component. Damage may be highly localized, see Figure 473, T in a 1000 Sig ethylene line before insulation removal. See Figure 474, close-up of TCUI of a T in Figure 473 after insulation removal. See Figure 475 CUI of a 30-inch CS butadiene line showing highly localized corrosion which could only be found by stripping the entire line. Note the 0.25 in, or 6.5 mm, diameter hole at arrow. See Figure 476 CUI of nozzle on a bottom head. See Figure 477 CUI of nozzle on a top head. See Figure 478 CUI of vessel wall. Note leak at arrow. See Figure 479 CUI at attachment supports and vessel head. Number E, in some localized cases, the corrosion can appear to be carbuncle-type pitting, usually found under a failed paint or coating system. Number F, telltale signs of insulation and paint/coating damage often accompany CUI. Corrosion under insulation, CUI, can have distinct appearances and morphologies that vary based on factors such as the material composition, insulation type, moisture conditions, and environment. Here are some key characteristics of CUI damage. Number 1 is localized damage. Localized damage, pitting corrosion, often appears as small, well-defined pits or holes on the metal surface. This is a common form of localized attack, particularly in carbon steel. Localized damage, localized blisters, blistering on the insulation surface can indicate underlying metal corrosion. These blisters can vary in size and may break open, exposing more of the metal to moisture. Number 2 is visible corrosion products. Visible corrosion products, rust formation. For carbon steel, visible rust generally appears as reddish-brown flaky deposits. This corrosion can be extensive but is often limited to the area directly beneath the insulation. Visible corrosion products, white or green stains. On aluminum, you may see white corrosion products, while copper alloys can exhibit a green patina due to corrosion, copper oxide. Number 3 is surface discoloration. Surface discoloration, areas where CUI has occurred may show discoloration on the outer surface of the insulation material. This can manifest as differences in color or texture compared to unaffected areas. Number 4 is insulation degradation. Insulation degradation, insulation may appear distorted, soft, or degraded, leading to cracks or splits. This can occur due to moisture retention from corrosion processes or thermal effects from constant temperature fluctuations. Number 5 is pooling and staining. Pooling and staining, moisture pooling at the base or along the seams of insulation can lead to stained or discolored insulation surfaces, indicating corrosion activity underneath. Number 6 is microbial growth. Microbial growth, occasionally, CUI can also be caused or exacerbated by microbial activity, leading to visibly slimy or discolored areas on the insulation or metal surface, referred to as microbiologically influenced corrosion, MIC. Number 7 patterns of damage. Patterns of damage, CUI commonly occurs in areas where the insulation is improperly fitted, at joints, seams, and where moisture can accumulate or where there are temperature fluctuations. The damage patterns tend to mirror the conditions that promote moisture accumulation. Number 8 is inspection challenges. Inspection challenges, CUI damage is often hidden beneath the insulation, making it difficult to detect without removing the insulation or using non-destructive testing methods. Therefore, regular inspections and maintenance are crucial. In summary, CUI damage typically appears as localized corrosion features such as pitting, rust, and surface blisters, often coupled with visible degradation of the insulation itself. The morphology can vary significantly based on the type of insulation and environmental conditions, making it essential for regular monitoring and maintenance to prevent significant structural issues. Corrosion under insulation prevention and mitigation based on API 571, Number A. Since the majority of construction materials used in plants are susceptible to CUI degradation, mitigation is best achieved by using appropriate paints/coatings and maintaining the insulation/sealing/vapor barriers to prevent moisture ingress. Number B. Flame-sprayed aluminum coatings have been used on carbon steels. The coating corrodes preferentially by galvanic action, thereby protecting the base metal. Number C. High-quality non-metallic coatings, properly applied to the surfaces to be insulated, can provide long-term protection. Number D. Thin aluminum foil wrapped on stainless steel piping and equipment has been used on stainless steels as an effective barrier under insulation. Number E. Careful selection of insulating materials is important. Closed-cell foam glass materials will hold less water against the vessel/pipe wall than mineral wool and potentially be less corrosive. Number F. Low chloride insulation should be used on 300 series SS to minimize the potential for pitting and chloride SCC. Number G, it is not usually possible to modify operating conditions. However, consideration should be given to removing the insulation on equipment where heat conservation is not as important. Preventing and mitigating corrosion under insulation requires a combination of proactive measures aimed at reducing moisture accumulation, selecting suitable materials, and implementing effective maintenance strategies. Below are key approaches for preventing and mitigating CUI. Number 1 is material selection. Material selection, corrosion-resistant alloys. Use stainless steel or other corrosion-resistant materials for piping and equipment that are vulnerable to CUI. Material selection, protective coatings. Apply high-performance coatings to the metal surfaces that act as barriers against moisture and corrosive agents. Options might include epoxy or polyurethane coatings. Number 2 is insulation design and selection. Insulation design and selection, moisture-resistant insulation. Choose insulation materials with low water absorption properties, such as closed-cell polyurethane or fiberglass with hydrophobic treatments. Insulation design and selection, vapor barriers. Employ vapor barriers in insulation systems to prevent moisture ingress, particularly in climates prone to high humidity. Number 3 is system design improvements. System design improvements, drainage solutions. Design systems with slopes to prevent water pooling, allowing drainage of any condensate or moisture that may accumulate. System design improvements, access points. Ensure that insulated piping and vessels have access points for regular inspection and maintenance, allowing for easy monitoring of hidden areas. Number 4 is regular inspections. Regular inspections, routine visual inspections. Conduct periodic inspections of insulated surfaces for signs of damage, moisture accumulation, or discoloration. Regular inspections, advanced inspection techniques. Utilize non-destructive testing methods, such as ultrasonic thickness measurements or thermography, to detect CUI without removing insulation. Number 5 is moisture control. Moisture control, temperature management. Maintain surface temperatures above the dew point to minimize condensation on insulated surfaces. Moisture control, dehumidification systems. In environments with high humidity, consider using dehumidifiers to control levels of moisture in the air. Number 6 is preventive maintenance. Preventive maintenance, scheduled maintenance programs. Implement a program for regular maintenance that includes inspecting insulation, repairing damage, and replacing degraded materials. Preventive maintenance, monitor environmental conditions. Keep track of environmental conditions, temperature, humidity, etc., that may contribute to CUI and adjust maintenance practices accordingly. Number 7 is application of corrosion inhibitors. Application of corrosion inhibitors, chemical inhibitors. Utilize corrosion inhibitors in the insulation system, particularly in systems where water is present, to reduce corrosion rates. Number 8 is employee training and awareness. Employee training and awareness. Training programs, educate maintenance and operational staff about CUI risks, identification, and best practices to mitigate it. Employee training and awareness, guidelines and protocols. Develop clear guidelines and protocols for managing insulated systems to reduce risks associated with CUI. Number 9 is documentation and monitoring. Documentation and monitoring, record keeping. Maintain documentation of inspections, repairs, and maintenance activities to monitor trends and identify areas of concern. Documentation and monitoring, risk assessment. Conduct regular risk assessments to identify high-risk areas for CUI and prioritize inspection and maintenance efforts accordingly. In conclusion, implementing an effective CUI prevention and mitigation strategy requires a comprehensive approach that includes proper material selection, regular inspections, effective insulation design, moisture control, and staff training. By addressing the factors that contribute to CUI, organizations can significantly reduce the risk of corrosion-related failures, ensuring the integrity and safety of their assets. Inspection and monitoring for detecting corrosion under insulation based on API 571. Number A. An inspection plan for corrosion under insulation should be a structured and systematic approach starting with prediction/analysis, then looking at the more invasive procedures. The inspection plan should consider operating temperature, type and age or condition of coating, and type and age or condition of insulation material. Additional prioritization can be added from a physical inspection of the equipment, looking for evidence of insulation, mastic and/or sealant damage, signs of water penetration and rust in gravity drain areas around the equipment. Number B. Although external insulation may appear to be in good condition, CUI damage may still be occurring. CUI inspection may require removal of some or all insulation. If external coverings are in good condition and there is no reason to suspect damage behind them, it may not be necessary to remove them for inspection of the vessel. Number C. Considerations for insulation removal are not limited to but include history of CUI for the vessel or comparable equipment, visual condition of the external covering and insulation, evidence of fluid leakage, such as stains, equipment in intermittent service, condition or age of the external coating, if applicable. Number D. Common areas of concern in process units are high moisture areas such as those downwind from cooling towers, near steam vents, deluge systems, acid vapors, or near supplemental cooling with water spray. Number E. When developing the inspection plan for CUI inspection, the inspector should consider areas that are most susceptible to CUI. If CUI damage is found, the inspector should inspect other susceptible areas on the vessel. Utilize multiple inspection techniques to produce the most cost-effective approach, including partial and/or full stripping of insulation for visual examination, UT for thickness verification, real-time profile X-ray for small-bore piping, neutron backscatter techniques for identifying wet insulation. Deep penetrating eddy current inspection can be automated with a robotic crawler. Infrared thermography looking for wet insulation and/or damaged and missing insulation under the jacket. Guided wave UT. Detecting corrosion under insulation, or CUI, is challenging due to the hidden nature of the corrosion occurring beneath insulating materials. However, several inspection and monitoring methods are effective for identifying CUI damage. Here are some of the key techniques employed in various industries. Number 1 is visual inspections. Visual inspections, surface examination, regular visual inspections of exposed insulation, joints, flanges, and fittings for signs of moisture, staining, or discoloration. Look for any signs of insulation damage or bulging. Visual inspections, inspection of insulation. Inspect the insulation material itself for damage, wetness, or signs of degradation, which could indicate moisture ingress. Number 2 is thermal imaging. Infrared thermography. This non-destructive testing method uses infrared cameras to detect temperature variations on the surface of insulated components. Changes in temperature can indicate the presence of moisture or reduced thermal efficiency, which might suggest CUI damage beneath the insulation. Number 3 is ultrasonic testing. Ultrasonic thickness measurement. This method involves using ultrasonic waves to measure the thickness of the metal from the outside of the insulation. A decrease in thickness can indicate corrosion underneath. Ultrasonic testing, time-of-flight diffraction, or TOFD. This advanced ultrasonic technique helps in assessing the size and depth of corrosion defects beneath the insulation. Number 4 is radiography. X-ray or gamma-ray inspection. Radiographic testing can be used to create images of structural components and detect flaws. However, this method may require the removal of insulation in some cases. Number 5 is magnetic particle testing, or MPT. This method is useful for detecting surface and near-surface discontinuities in ferrous materials. It requires removal of insulation only from sections needing inspection. Number 6 is eddy current testing. This technique is effective for identifying wall loss in conductive materials. It can be adjusted to work through insulating layers, enabling inspection of surfaces without insulation removal. Number 7 is moisture detection. Moisture meters. These portable devices measure moisture levels within insulation and can help determine areas where moisture may be present. Humidity sensors. the use of sensors or data loggers to monitor humidity levels in areas near insulated equipment can help predict and prevent CUI. Number 8 is dye penetrant testing. This method involves applying a penetrant dye to the surface, which seeps into any surface cracks. After a specified dwell time, excess dye is removed, and a developer is applied to indicate the presence of cracks. While it is primarily for surface defects, it can help detect failure points leading to moisture ingress. Number 9 is corrosion rate monitoring. Corrugated coupons. Install corrosion coupons adjacent to insulated systems to assess corrosion rates in real time. These coupons can be periodically removed and evaluated. Electrochemical sensors. These can provide real-time monitoring of corrosion activity and help in assessing the effectiveness of corrosion protection measures. Number 10 is remedial actions. If any signs of potential CUI are detected, careful removal of insulation can be performed for thorough inspection. After treatment, appropriate measures, such as repairs, coating, can be made before replacing the insulation. In conclusion, a combination of these inspection and monitoring methods is often employed to effectively detect CUI. Regularly scheduled inspections, coupled with various non-destructive testing techniques, can help identify areas of concern before significant damage occurs, ultimately extending the lifespan of insulated assets and reducing maintenance costs. Thank you.